All right, welcome everyone to the next HRA webinar. We're going to be covering the top 10 myths surrounding VRF systems, and we're going to be doing so with Jose de la Portilla. You've known him before. He's done a few of these, and he's graciously come back to lend his expertise. Jose is the National Training Manager for Samsung HVAC. He's been in the HVAC industry for nearly 30 years, specializing in service, installation, technical support, training, and it's been his passion for the past couple decades. He also serves as a member of the NATE Technical Committee and is ACCA certified in residential system design. So all that to say, he's the guy who can talk us through this. And Jose, why don't you introduce yourself?
All right. Thank you so much, Matt. Really appreciate it. And I want to thank everybody for coming today. As Matthew said, we're going to be covering the top 10 VRF misconceptions that are out there. And really what these misconceptions are things that people just don't understand or are worried about before they start getting into the VRF industry.
Awesome. You know what? I'm going to turn off my camera, leave it to you. Just a quick reminder again, this is being recorded, so you can catch it on HRAI's YouTube page later and share the link with whoever you'd like. And also, too, you can ask questions during the presentation in the chat field here, or there's a Q&A field as well. So I'm going to get out of here, let Jose do his thing. Thank you so much.
All right. Thank you so much, Matthew. Okay, so like I said, we're going to cover the top 10 misconceptions surrounding VRF. In our last session, we discussed what is VRF and gave you the insight into everything you need to know about variable refrigerant flow systems. Today, we're going to focus on the top 10 major concerns or misconceptions people have about VRF systems and how we overcome them. Okay. A lot of it is just a lack of experience or knowledge. So we're going to address those today. These are the 10 items we're going to focus on. But without any further ado, we're going to jump right in. Again, as you have questions, throw them in the question and answers pane. And we'll do our best to answer them right here live on screen so that we get you your answers as soon as they come in. Now, the first misconception people have is that VRF systems do not perform well at low ambient temperatures. Well, that really couldn't be farther from the truth from the technology that they have. Now, you do have to design the systems based on a proper load calculation. And if you're in a cold ambient situation, a low temperature situation, these hail guards and wind guards that you see are just instrumental or pivotal for their success. Because as the gust of winds come by, the cold air is blowing by, you don't have to worry about wind chill effect affecting the coil. So that's one way that they perform at low ambient conditions. Now, you want to design the system for worst case conditions, but you also may want to look at bin data to see historical values, right? And you want to see what the coldest temperatures you see at different points of time. Why did we design for worst case scenario? Well, what if it happens that on that day, you drop below that worst case condition and you don't have a system that can meet the needs or keep the building online? So how do manufacturers approach, or how do people, when they're designing systems, tend to approach low ambient conditions? Well, there's a couple things that they start with. Okay, great question. What does VRF stand for? That stands for variable refrigerant flow. And we covered this in the last session, but what that means is that instead of having a system that's on or off, like you would see with unitary product, or maybe it's on and has two stages of compression, this is completely inverter driven. So the product can ramp all the way down and all the way up and change its speed to change its capacity to whatever we need at any given time. Great question, Monica. Thank you. So now let's talk about what people do when they're designing a system when it's really cold outside and they have to design to -13, -5, whatever those low ambient temperatures are. What do people do? Well, first off, when you're looking at VRF systems, the first thing people used to do is add supplemental heat. Well, that just added to the cost of the jobs and the complexity of the controls, because they would add heaters in the systems and supplemental or boilers and other things like that. If it's not really needed, that's added cost and added installation time. So the next thing people would do is they would oversize their VRF equipment, and they would oversize it so that they always had enough capacity even when it's cold. That creates problems, though, when you don't need all that capacity. These systems are inverter driven, so they'll ramp down. And if they stay at low frequencies for long periods of time, we have to worry about oil return. We have to worry about performance. We have to worry about reliability. So another way you can overcome low ambient temperatures is every VRF manufacturer gives you the ability to take that outdoor unit and put it inside a building. You have some ventilation, you have some louvers that bring fresh air into the building to go across the coil. and then they discharge air outside through ductwork placed on top of the units, like you kind of see on Company X down there on the lower right-hand side. That's another option, but here's the best one. The best one is to utilize a specialized high heat VRF system. Now, I can't speak for everybody's performance, but I can tell you that Samsung, our high heat solution, will give you 100% capacity down to -13. Now, a normal heat pump just gives up the ghost right around 17 degrees, and we really design them for an ambient temperature of somewhere around 47. But this will give you 100% heating capacity all the way down to -13. And what this does is it gives us the ability to overcome that misconception that they don't work well when it's cold outside. Now, the other thing that you have to look at is, okay, we give you 100% heating capacity down to -13. After that, we start to derate. But the difference is not every company derates at the same value. Okay, so if you look at, excuse me, if you look at Company A here, they might actually start derating right around 4 degrees, and that temperature continually drops, or that capacity continually drops, so that at -13, they might only be at about 79, 78% capacity. Well, our max heat product, like I said, you want to get a good low ambient solution, will give you 100% heating capacity at -13. That's how we can overcome that myth of it just doesn't work at low ambient temperatures. Now, another way this product works really well in low ambient temperatures is that if you have a larger capacity system, you would create a module. And a module is simply one large outdoor unit that's made up of 3 or 2 individual outdoor units. They're piped together, and so they act like one unit. Now, all heat pumps have to go into a defrost. But what we do, and what most manufacturers do, is utilize what's called rotational defrost. So that might mean that only one of these units, what doesn't mean it might mean, it means that only one of these units is in defrost at a time, giving you extra heat or still giving you heat from the other 2. So maybe the unit on the left goes into a defrost, the middle and the right are still running. Okay, now the one on the right goes into defrost, you have 2, on the left-hand side that are still heating. And then finally, if the middle one goes into defrost, the other 2 heat. You can't do that with other systems. If you have multiple splits, then you could rotate the defrost on them if you had the ability to do so. Most defrosts are either time and temperature initiated or they're demand defrost, but they're not going to talk to each other if you have splits or package units up on a roof. This modularized system with 3 outdoor condensing units definitely talks to each other and gives us that rotational defrost to make sure we perform at low ambience. Now, we have an advanced defrost operation, and most manufacturers have something. Samsung's, we call it intelligent defrost. So unlike a normal defrost that says, okay, it's this temperature coil, and it's been this much time, let's go into a defrost whether we need it or not. Intelligent defrost utilizes logic that says, okay, let's see how we're running. Let's look at ambient temperature. Let's look at coil temperature. Let's look at runtime. Let's look at amp draw on the condenser fan motors and decide when exactly to defrost based on the fact that a defrost is really needed. So that's time, temperature, air resistance across the coil. Now, here's what we see. If you look at a conventional defrost and then you compare that to an intelligent defrost, the conditions we tested this at are on the left-hand side. If we look at total heating run times over this 10-day test period, a conventional unit was in defrost a conventional unit was in heating only 193 hours, where intelligent defrost was in heating for 202 hours. And the less time we spend in defrost, the more time we spend heating. Look at the average time between defrosts. Conventional systems, every 10 hours, they were going into a defrost. Intelligent defrost systems were only going into a defrost every 101 hours. So again, you're going to spend more time in heating, having less of a concern about low ambience. Now let's take a look at the number of defrosts that occurred over the same period. 19 defrosts occurred on a conventional unit utilizing a demand defrost circuit or cycle, only 2 on intelligent defrost. The less time we spend in defrost, the more heat we have at low ambient temperatures. But if that's still not going to work for you, right, there is solutions. Go to water-cooled units. And as long as we keep the water temperature a consistent temperature, we have 100% capacity all the time. So that's a solution out there for you. Here's this example I showed you where you can put these things in mechanical rooms and put ductwork right on top of them. You can control the temperature or block some of the winds, and then you can have the discharge be pushed out because these fan motors have the ability to push static or push air out with static pressures of 0.3, 0.4 inches of water column. If you're looking at a unitary split heat pump system or even some like commercial heat pump systems, the static might only be 1/2 inch. Well, these are almost 1/2 inch just on the condenser fan motor. Those other systems, 1/2 inch, are typically on the blower, which is more powerful. So you have the ability to modify that system. All right, now worst case scenario, you're like, you know what? I really don't know if this is going to perform. I don't know if I trust it. Reach out to the manufacturers. If they offer a CFD, which is computative fluid dynamic analysis, you can give them plans. You can give them size, you can give them capacity, and they can run electronic simulations to tell you exactly how that's going to perform. So we get a drawing, we run it through a computer, 3D modeling, we define the structure, the heat load, and then the output shows you, okay, here's what's going to happen. Here's what the heat flow is going to look like, whether that's air going to recirculate or it's going to be too cold, whatever that looks like. So there's systems to help if you're not 100% confident. Low ambient cooling hoods. Let's say you need cooling even when it's cold outside. Maybe you're looking at a mechanical room, a server room, equipment rooms where you've got mechanical machines that you need to keep at a critical temperature. Well, by the addition of adding low ambient hoods, you can get 100% cooling capacity at temperatures somewhere between -9 and -13. That's right, -9 or -13 by putting these low ambient cooling hoods on that direct the airflow away. So we'd restrict the wind chill, and then they throttle down the louvers and slow down the fan speeds to make sure that we can continue to operate at right operating temperatures and pressures to give you that performance all the way down to -9 or -13. Moving on to misconception number 2. VRF systems are complicated to design. Now, people typically look at these systems and they say, you know what? There's outdoor units, there's indoor units, there's mode control units or branch boxes, there's Y joints, there's headers. I can't keep up with all of that. I can't design that on paper, and you don't have to. VRF manufacturers offer unique software that provides solutions for you. It's going to remove the guesswork because they're going to do system matchups. Here on the right, you see the outdoor unit, you see the indoor units, you see the green boxes. It says, hey, these are approved. Okay, this is going to work. They lay out your refrigerant piping. So you tell it how many linear feet of piping you have, the capacity of the outdoor units, and it says, okay, because of that length, because of the number of elbows, you're going to need this much copper. Oh, and because of the capacities, they need to be this size. It's taking the guesswork out of it. You're not manually sizing line sets. Right? Power wiring is given there with minimum circuit ampacities and maximum overcurrent, so you can design breakers, you can select wire. You got your control and wire layout schematic, so you can get power wiring and control wire to your engineer or to your controls person on the job to lay it out appropriately based on the design. And when you put these in, instead of being like traditional unitary split systems where you have to weigh the additional charge in based on length, and then you have to check superheat and subcooling to see how it's performing, these give you the exact amount of refrigerant charge you need to add. Weigh that charge in, turn the system on, it's ready to go. All right, and it gives you ability to select your system accessories and put it all on one report. So when it's time to order the supplies, you know you didn't leave anything off. So also the design software will offer, at least Samsung's does, will offer a CAD component to where you can select a button and open it up, and it'll work just like AutoCAD. Import your DWG files, see the building layout, drop your units in place, select your units, and it'll calculate line length for you and give you path and orientation. All right, so that's the second one. The second one is they're complicated to design. They're really not if you utilize the factory software. Now, the third misconception, VRF systems are complicated to install. And again, not really so. If we take a look at the fact that we're utilizing a lot of ductless products, now we may have some ducted units, but for the most part, there's a lot of ductless products, whether those are cassettes or consoles or wall mount units. You have a lot of ductless stuff, which means minimal to no ductwork. So you're going to have a lot less labor installing big, bulky metal ductwork. The control wiring, instead of having everything home run back to an outdoor unit, the control wiring is daisy chained because the system completely communicates. So that means that the communication wire goes from the outdoor unit to the first indoor unit. Then instead of going from the second indoor unit back outdoors, runs from the first to the second unit to the third, so on and so forth. So you have what we call one daisy chain network all the way through. The schematics are given to you by the design software. The expansion valves that open and close to allow the refrigerant, they're factory installed. No field installed expansion valves. And when you're looking at running the construction, you're running small copper lines instead of that big bulky ductwork. And those copper line lengths are also a big benefit to us because we can greatly exceed unitary product line set lengths, where maybe with a unitary split, whether it's a 5 or an 8-ton split, you might be limited to around 150 feet out of the box. And then maybe if you utilize some design special considerations like double suction risers, inverted traps, things like that, you can go a little bit longer. Here we're talking hundreds and hundreds, maybe even thousands of feet of copper allowable for you to run this job. So it gives you greater installation flexibility. Now, if you're going to do what we call heat recovery, that's where we talked about on the last webinar about the ability to provide heating and cooling simultaneously from one outdoor unit. What you're going to utilize is what we call a mode control box, an MCU. Other people call them a branch box, a branch selector. There's several different names for them. But what this does is, you've noticed here, refrigerant comes in on one side and it leaves on the other. And then there's a series of ports where it directs either refrigerant for heating mode or refrigerant for cooling mode to indoor units. And there's various offerings. So you've got, any of them that range from up to 1 up to 18 ports. So 3 pipes in, 18 ports coming out to go to different indoor units, right? The sound levels and the sizes are going to vary from manufacturer, so you want to check that out. A cool thing about Samsung MCUs that makes the installation even more flexible is that if you have this mode control box and all your piping is coming off to the right and you need to come out with more ports, but you want to go to the other side of the building, get another mode control unit. You pipe it in series with this outlet piping, but rotate it 180 degrees. This way, the units that need to go to one side of the building are coming off the left, the other are coming off the right. That's going to reduce the amount of copper that you need and make it easier to install. Now, some of these mode control boxes, you'll need to manually address them. You're going to have to get up on a ladder and change some switches. Samsung systems, they do what's called auto pairing and auto addressing, where when the system starts up, it looks for mode control units, looks for indoor units, figures out how many they are, assigns unique addresses, and then pairs the indoor units to the right port on the mode control units, making it very easy to install. You're not chasing an indoor unit and wondering where it goes back to and changing buttons and wires and configuration. Okay, so we'll move on to mode control, or to misconception number 4. And that's that systems are unreliable. And if we step back and really analyze the technology that's in VRF, that couldn't be further from the truth. Here's what happens. Instead of standard PSC motors that are on or off, or maybe a 3-phase motor controlled by a third-party variable frequency drive, what you're going to get in a VRF system is motors that are designed by the company that designs the product, so they communicate. They're going to be brushless DC, digitally computated motors. Brushless meaning there's no arcs, there's no magnetic rotor loss. You're going to have a very, very efficient motor. You're also going to have a system that can ramp up from low to high speed. So unlike a system that starts up and pulls what we call lock rotor amperage or high inrush current because it's on or it's all or nothing, these start low and ramp high to control the maximum or the starting current, but also to make sure it ramps up slowly, because the hardest thing on any motor is start and stops. Now, throughout the system, VRF systems are going to not shut off most of the time, and that's okay. People get concerned. The system's been running all day long. That's what it's designed to do. If we run that system all day long and modulate its capacity based on the load inside the structure, then that system runs all day. Less wear and tear, because one of the hardest things, again, start and stops. But also, if we want to make sure that the temperature inside the space doesn't fluctuate all over the board, keep the system running to constantly keep that air in contact with an indoor coil that's making sure that the heat is appropriate and making sure that the cooling in the space is appropriate. These reduction in start and stop times and system modulation, this all makes it more reliable than a unitary product. But we also have to look at the controls inside. Unlike a unitary product, which have contactors and relays, and maybe an integrator to allow it to talk to a building management system, these actually have the ability to look at how they're running. So just a few things up at the top here. You can see that they monitor their voltage, their amperage, their temperatures, and there's probably hundreds of points of temperature measurement in there. It monitors the RPMs of the motors, outdoor conditions, set points, user entry values. They want it hot, they want it cold. It looks at all these values. And if some of them go out of range, the system doesn't run unsafe. It actually will generate codes. It'll slow itself down. It'll change its staging to say, you want this, but because of a problem with an indoor unit, I can only give you this. and it'll generate a code for the servicer to get out and take a look at the system. So between the other parts that are brushless DC, they ramp up their system modulation, reduce wear and tear. You got a system that's so smart, it's constantly checking everything about itself to know if it should run or how it should run based on the conditions it's seeing. Okay. Again, not unreliable, more reliable is what you're seeing from these two slides. Okay. And again, if you have questions as we go, throw them either in the chat box or throw them in the questions and answers box. I'm trying to keep my left eye on it while I talk to you out of the right eye or look at the screen through the right eye. So we'll do our best to get you the answers however we need to. Okay, we're going to move on. Misconception number 5. Misconception number 5 is VRF systems have a very high overall cost. It's not the case. What people think about when they say high overall cost, they're typically focusing on initial purchase price. While it's true, the initial purchase price of the HVAC system may be a little bit higher, total life cycle cost is going to be dramatically lower. And again, that's due in part to we're not installing big bulky duct work. We're not having the guys up on lifts, strapping it to the ceiling, worrying about the sheet metal. It's designed right. We're not doing that. Because we're not running ducted as much duct work, we can account or we cannot account for ducted heat loss and heat gain, as well as ductwork that might be placed in an unconditioned space, which adds a lot of needed extra capacity to an HVAC system. I mean, if we go ductless, we could probably reduce the size of the equipment in some cases, a ton, 2 tons or more, because of that additional load that's generated by duct loss and gain, duct leakage, and ductwork being placed in unconditioned spaces. Okay. How about this? You don't need to condition rooms that don't need to be conditioned, right? If you had a room and you set it back far, you set it back, a big drop back or a big droop or differential in room temperature because nobody was in there, then when the system did turn on, it had to try to tackle all that load, and that motor can only do what it can do. VRF systems can ramp. So what happens is we control the compressors with frequency. The normal frequency that an electric motor feels or sees is 50 or 60 hertz, 50 or 60 cycles per second. We take the voltage and we turn it backwards, and that helps the motor run. Well, VRF systems don't just run at 60 hertz. They may start and ramp up to 60 hertz when they need to, but if they need a lot of capacity, they can ramp up to 140, 160 hertz to get fast cooling, fast temperatures, or fast heating. They can also, if it's low temperatures and it's low conditions outside, not a lot of load in the building, they can ramp all the way down to maybe 10, 14 hertz. And what that's going to do is change its operating characteristics and change how much money it takes to run it. Okay. Again, you don't need to condition the unoccupied spaces. And that system modulation, instead of starting up and down, is going to reduce your energy consumption as well. So let's just take a look at energy consumption. So if you're just looking at EER, energy efficiency ratio, and you're looking at a 6-ton package rooftop unit, and you're looking at this low ambient solution outdoor unit. And I picked the low ambient solution outdoor unit because since it's designed to work at minus 13, you would think it's going to be an energy hog. Not necessarily the case. Notice the EERs are very close. Technically, the 6-ton rooftop ekes us out on IEER, but that's at peak load performance. And remember, when we talk about peak load, traditionally, we're only at peak load 1% of the time, meaning that 99% of the time that equipment's oversized. That 6-ton rooftop can't do anything about it. The VRF can. So we have to look at a different rating. And that rating we're going to have to look at is IEER, and that incorporates part load performance as well. So if we're looking at that 6-ton rooftop, its IEER is 11.3. Again, part load performance. It really can't do anything because it's on or off. The 6-ton variable refrigerant flow unit, its IEER is 29.3. What does that equate to? Well, right around a 40% reduction in energy consumption just by switching from one brand to another. So if we're talking about overall cost, life cycle cost, the entire cost of the system, yeah, the initial purchase of the equipment may be a little bit more, but when you look down at all these different variables, the life cycle cost is going to be dramatically less. That's just something we have to communicate. When we're talking to a building engineer, when we're talking to an architect, when we're talking to an end user, and they're like, why? This is going to cost more money to install. We need to share with them how much money they're going to save in energy consumption and labor in installing the VRF versus other products. Now, if we really want to dive into this, we can go even deeper. Because as we talk about VRF systems not having a high overall cost, look, if we've got an engineer building the system, we can get in on the ground floor and talk about going VRF. That building is going to cost less to build just because of VRF. The other trades are going to design around our specifications, right? So let's take a look at what those are. You're going to have smaller plenum height, which is floor to floor heights, because you're not running bigger ductwork. You're running smaller copper lines. You don't need as much space, more rentable space, right? Less cost making a bigger structure. You're going to have lighter and smaller equipment. So the roofs or the ground or the platforms don't need to be designed to handle as much weight as a typical product. Now, if we take a look at it, because of its inverter-driven technology, you're going to have lower minimum circuit ampacities, so smaller wire sizes, and lower MOCPs, maximum overcurrent protection, smaller breaker sizes. Okay. It's also going to simplify your planning because you're going to have this software to tell you how everything goes and where it goes. And you're going to have installation efficiency because it's going to cost less to install with all those things we just talked about. But also, one of the biggest concerns in a commercial building is precise temperature control. You've probably been in that building where you're on the same floor and people on the perimeter are hot because of the solar gain, right? Mean radiant temperatures coming through the glass. People in the core are cold. You've got a thermostat in the core, not on the perimeters, and people are uncomfortable because that thermostat keeps getting bounced back and forth. Okay, not with VRF. With VRF, we're going to have individual indoor units. So the perimeter, they can select whatever temperature mode they want and temperatures they need. Inside, or the core has their own controllers to tell the system how they want it to operate. So this is really going to reduce the overall cost. All right, moving on to misconception number 6. That's that VRF systems, because they're ductless and we have different indoor units, they can't manage outside air, and we really need to be able to build the system around fresh air requirements. So that's not true, though. If you go to a ducted unit, like you see here, these 2 square ducted units, everybody makes 4-way, they can utilize fresh air. There's a knockout on the side of the unit. It's typically about a 4-inch round knockout. You can bring fresh air in to that knockout. Now, you want to filter that air to avoid the unit from getting so dirty. And because these coils are positively pressurized, you will need a little booster fan to overcome the static in the unit. But you can accomplish, or you can accommodate, a large amount of fresh air depending on the size. I mean, for example, if we look at the medium chassis unit here, and that booster fan is able to create enough static pressure, say about a 0.28 static pressure, then we can get about 47 CFM directly into that cassette unit. Okay. So you can bring air right in the back of a cassette unit. If you have a ducted unit and you've got ductwork, treat it just the same. Bring air right into the back of the ductwork. Okay. Another option, though, that people look at, and this is oftentimes what we see people choosing in buildings now, is to decouple the ventilation. And what I mean by that is have a separate system to handle ventilation than you do the outdoor or the HVAC system. Now, and that's another huge gain for us. Ventilation adds a lot of extra load to the load calculation because of the outdoor ambient temperatures, the relative humidity, or what we call the wet bulb of the air, and those are going to affect the load, meaning you have to upsize the HVAC system. Decouple that, and you don't have to upsize the outdoor unit or the VRF system, the HVAC system, quite as dramatically. Okay, so this gives us some really neat flexibility. So how about this option first? Over here on the right, you've got your VRF unit sitting on the roof. You've got multiple indoor units throughout the entire structure. It's a very simplified look. What about using a ventilator, a energy recovery ventilator or a heat recovery ventilator? They have a core, they can bring fresh air in, they can temper it, and then they can clean and dehumidify the air before it gets into the indoor unit. And what's going to happen is you see this fresh air duct going into the structure, it's ducted right into the cassettes. But we're getting pre-treated air, so we don't have to tackle the load from outside air in our HVAC design. And so maybe we're pushing fresh air into these cassettes, and then we have one exit grill, one exhaust, one return grill for the fresh air to be exhausted outside. That's one way. Okay. Another way is to completely separate it and not even duct into the units. You can do that with an ERV, but here I want to show you another option. Here's the VRF outdoor unit with its indoor units. And here's a VRF outdoor unit tied to a coil, an air handler, an indoor air handler that has both a cold coil and a hot coil. This is known as a dedicated outside air system or a DOAS system. Now, all this unit over here with this indoor unit, all it's designed to do is bring neutral air. So somewhere around 70 to 75 degree air goes into the structure. But because we have a cooling coil and a heating coil, not only can we temper the air up to 75, that air first passes across a cooling coil, as you see on the left here, and brings out all the humidity. That air that's dehumidified is now brought to a reheat coil where we reheat it back to neutral state with no humidity to be concerned about. You can duct that into the back of your cassettes, or in this example, we duct them into their own grills, maybe in a hallway in an adjacent area, and we have its own grills that go in. And then we utilize the building itself for exfiltration, right? Exhaust fans, whatever that looks like. So if we move on, misconception number 7. Misconception number 7 is that VRF systems are just hard to service. That's not true. Why it may have been years and years and years ago, and maybe it even started on the mini split world, it's not as complicated as you think. I mean, here's the typical wall mount unit. People think those are horrible, right? They're hard to service. They're hard to put in. Well, this bottom panel, it snaps off with interlocking pieces. And then one screw here and one screw here, I can take every piece of plastic off the unit. By doing that, I can see the control board immediately. I can pull the drain pan out of the way without any screws and get to the coil to clean the coil. I'm sorry, the coil and the blower to clean the coil and the blower. I can also clean out the drain pan, but look at that control box. Not only can I see it, but I can push down on a tab, pull the control box off the side of the unit and look at it in my hand instead of standing on the top of a ladder and trying to see it and look at it or put test points on it. So wall mount units alone become very easy to service, but let's talk about cassettes. So here's a cassette. This happens to be our 360 cassette. Same functionality for a lot of 4-way cassettes as well. You drop the return air panel, and through here, you can get to the control boards, the blower. You can remove the blower and get to the coil. You can remove the blower and get to the electronic expansion valve. You can gain access to every single thing in the unit from the bottom. The only thing you need to get on the outside for is the piping and the high voltage coming in, right? But you can still get to the high voltage. It's wired on the board. But if you need to change out the unit, you got to go to the outside of it. But 99% of the product or components are all accessible from the bottom of the unit. Now, ducted units, if you're utilizing the pancake style units or the lower profile units, I mean, look, most of them you can gain access from 3 different places. From the top, you can get into major components. So you can see here the blower wheels, the fan housing, the circuit boards, condensate pump. You can do the same thing from the bottom. And then on the side, I can get access to the copper piping and the control board, the electronic expansion valve, and a condensate pump's float switch if I needed to. Another thing that makes VRF really, really easy for service work is something that Samsung utilizes. We utilize an EEPROM chip. What does EEPROM stand for? Electronically erasable, programmable, random onboard memory. And you didn't need to know all of that. But here's what an EEPROM chip is. It's like the SIM card for HVAC. So every unit that comes out of the factory has an EEPROM chip on it, and that stores everything about the system. Its size, its capacity, how you configured it, your option settings, where the equipment is, line set, all of that information, it stores on that little EEPROM chip. Something goes wrong, a board goes down, and you want to put a board back in, you're worried about programming these hundreds of settings or whatever you have in there, it's not a problem. Take the old board, pull the EEPROM chip off, go to your new board, plug the EEPROM chip in, system starts up like it never had a problem. Okay, so it's equivalent of a SIM card. The system now knows what it's doing. There's no recommissioning process. And service software makes this a breeze. So let's say you have a complex VRF system. You got, 50, 100, whatever, 64 indoor units, whatever that looks like. You've got the units up on the roof. You want to be able to see its runtime, how it's staging, how it's turning on and off, how it's changing from heating to cooling. You want to see ampacities, valve positions, right? Instead of having to go and test all that stuff, you hook up a laptop with a little converter, you dial into the system, and every single thing you could ever need can be pulled from some design software or from some service software. So you can see everything about the system, but also let's say that you need to make a change to every single indoor unit. Whether that is you need to select them so that they turn the chime off when you turn the system on or off. Well, if you want to do that, instead of going to every unit and smashing buttons on a controller, hook up your service software, hook it up to the outdoor unit, and change everything at one single time. That's right. I can go to the outdoor unit and I can apply the changes to every single unit that's out there. Okay, so we had a question come in. What is the life expectancy of VRF systems? Because that's point one. So I can't tell you exactly what it is, but I can tell you that based on some industry stuff here, especially in the US, ASHRAE has looked at that, and they are estimating somewhere around 10 to 15, but depending on the operating conditions, it can go even greater. Okay, I've seen them install for quite a while. By what percentage does the upfront cost increase if VRF is utilized compared to conventional HVAC systems? That's a really good question. What is the initial price? I can't tell you because I'm not on the pricing side. And as you look at different manufacturers, they're going to have different rates. And also there'll be multipliers for contractors and engineers that are doing different projects. I can tell you that it used to be significantly higher. But right now, we've seen our sales team go out and do comparisons, and VRF is almost neck and neck with unitary products. So while I can't give you dollars, I can tell you that that margin between the purchase price of VRF and unitary has dramatically dropped to where they're almost comparable. Okay. And the third one, what would be the energy cost savings on the long run when utilizing VRF? Well, I think that goes back to the slide where we talked about IEER. And if you take a look at that, that's a 40% reduction in energy consumption. So we have to account for that. We then would have to look at servicing, right? And of course, service, that all revolves around how it was installed. If this system is installed properly, there's going to be very little service that needs to take place. And if there is service that needs to take place, the contractor, the builder, the maintenance engineer, they'll know of it through service codes or alarm codes or alert codes way before the system completely shuts down. Because one of the hardest things to account for is when a system goes down, especially in a commercial building, and you have to bring in backup systems or portable systems to keep people comfortable until the system's repaired. This thing is going to be able to run. It's going to be able to protect itself, run itself longer, and let people know right away. Okay, so I hope that answers some of your questions there, and a great question. So thank you for bringing them in. We were talking about the ability to take this laptop and this converter and dial into the outdoor unit and be able to program every one of these indoor units. Yeah, this is one of my coolest features, being a former service guys. Middle of the summer, I don't want to be on that roof. I need to change the indoor units. It doesn't matter. Go to any of these indoor units, sit in this nice, comfortable room here, get your ladder out, hook up to that, and make the change to everything else in the building, including the outdoor unit. The service software really makes it a breeze. So it's easy to service. Okay, so that kicks us over towards misconception number 8. And that's that, yes, we tell you we can do heat recovery. You can simultaneously heat and cool the building at the exact same time. And the misconception there is, I don't need heat recovery. I never had it before. Right. And so people had to deal with it. But giving them the flexibility of having heating and cooling at the same time improves system comfort and improves efficiency, right? We can utilize simultaneous heating and cooling to do what we call waste heat transfer. So if you look here, I have all these units in cooling, right? They're sucking heat out of the spaces. They're absorbing the heat into the refrigerant. And then normally they would push that refrigerant outside. We'd reject the heat and it wouldn't really change how efficient the system is. But since I have these units in cooling that are absorbing heat, and the perimeter here, where the glass is, where the snow's out by the window, where it's cold, we're taking the heat from these zones and dumping it into these zones. And what that does is it gives us the ability to run the outdoor unit just low enough to move refrigerant without having to create a ton of extra heat. Now, that waste heat that we can use really makes it energy efficient, but it also gives us the ability to have that flexibility. If you think about a commercial building, again, if it's an all glass building, it's cold outside, there's snow on the ground, those exterior walls are going to be extremely cold because glass is not as good of an insulator as the concrete or whatever the building is made out of. Also, you have mean radiant temperatures, which make people feel colder because of the amount of surface area around them that's absorbing heat. So those perimeter, you're going to want to heat. But then look here in the core, we've got conference rooms, we've got cubicles, we've got printers, we've got computers, we've got lights. These folks are going to be warm. So we can cool these spaces at the same time as these. So people say, okay, I get that concept, but do I really need it? What buildings does it work for? So let's take a look. Here's a commercial building. There's multiple stories. On the rooftop, there was a restaurant, 70% glass floor to ceiling. Restaurant equipment, lighting, bodies, masses, people, you're going to need cooling almost all year long, right? Down here at the bottom, right? You got a downstairs shopping space, lights, heat, equipment, computers, people moving through. It's going to need cooling. But look in the middle of the building, right? Somewhere between those floors, there's office spaces with cubicles, right? They might need cooling. They might not need cooling. They might want heating because there's not a lot of movement. They're sedentary. They're sitting at a desk. So a building like this is perfect for heat recovery because we can do it without adding a supplemental system. Or we can do it without running a zone system that just shuts off a zone when it doesn't need airflow. When it finally switches back to heating, they get airflow, again, affecting occupant comfort. Now, schools are notorious for having hallways that during the hallway periods or change between the times, they're packed with people. It's warm, right? The lighting is in there, right? Then you've got reading rooms, cafeterias, right? Which have a different heat load profile, auditoriums, gymnasiums that don't need, much, but even when it's cold outside, they need heating. Computer labs, they need cooling all the time because we don't want to have the computers over a heat. Server rooms, classrooms. Notice all these different load profiles as we look at these spaces that will give us the ability to meet their needs with heat recovery. Medical buildings, the lobbies are one temperature. Patient rooms are typically kept a lot colder to help prevent some biological growth that may occur. Operatories are kept cold and clean. Medical equipment rooms, they all have different load profiles and will need a different heating or cooling setup. So we can do that with heat recovery, right? Hotels, you get it. Hallways, guest rooms, conference rooms, dining rooms, laundry rooms, offices, lobbies. They're all going to need something different. They can be very dramatically different from each other, and they could all be needed at the same time. Again, you couldn't do that without adding separate systems until you utilize heat recovery, right? Heat recovery can do that for you. Apartment condos, right? A lot of people are using VRF systems. They're individually giving indoor rooms and gyms control of indoor units for that VRF system. Well, heat recovery makes sure that gym area is always cold, right? The dining rooms are cool. The sitting rooms, maybe the bedrooms get heat, right? And with individual apartments, you can also use controls to track individual energy consumption rates off of that one VRF system for tenant billing, right? So they can utilize one outdoor unit, multiple indoor units, and still bill their tenants individually for their energy consumption. And here's just a building, right? This is a larger home. This is an animation, a drawing of it. But let's take a look at some things here. Upstairs, we're not really worried about it right now at this point in time. But we have a kitchen. They're cooking. They need cooling. Media rooms, lights, projectors, sound equipment needs cooling. A bedroom, right? Getting ready to go to bed, you might want some heat. Studies, only one person in there reading, doing some work, whatever that looks like. They need heating. Sitting room, you're just sitting and relaxing, right? You're going to need heat. And this is all happening at the same time, which can all be done with heat recovery. All right. So moving on to misconception number 9. And that's that VRF controls are not flexible. You got a different controller. The buttons don't look the same. They don't do everything. Well, that's wrong. If you look at like advanced controllers, they have color screens, dual set point, built-in room temperature sensors. They have advanced heat pump auto changeover settings. They're 7-day programmable. They have occupied and unoccupied modes. You can control up to 16 indoor units with one controller. So you have a big gymnasium. You've got all these indoor units. They all have their own return air temperature sensor, but you want to command a set point and an on and off to every unit. One controller controls up to 16. These controllers can do energy monitoring, and they can be used to configure the equipment as well, right? So that's just one thing that you can do. But you can do more. So let's say that you have a building owner who wants to utilize their thermostats, and maybe they like their thermostat because they like the app that comes with it, whether that's a Nest or an Ecobee or a Ventstar or a Honeywell, any of those brands of thermostats that have an app that the homeowner can use. You got a VRF system. They don't talk directly because their communication protocol is a digital signal and it's DC voltage, right? Well, doesn't matter. Put on a thermostat adapter. Put this on. The thermostat adapter still controls the VRF unit, still get full system modulation. You still get the heating or the cooling. You get it to ramp up. Everything we've already talked about. But the device telling it when to start and stop is a traditional thermostat. So to the end user, they just have a regular thermostat like they're already used to. Okay. This thing can energize emergency heat, supports single-stage, two-stage cooling thermostats, multiple fan speeds, just about anything you need, making it extremely flexible for a third-party control. Now, you're in a building, right? And in that building, they already have a building management system. It may be older, it may be antiquated, but they want it, right? So it may be BACnet. Well, they can get a BACnet gateway. Maybe it's lawn. It's a really older building, or it's a military source site, and they're utilizing LawnWorks. We'll give them a lawn integrator. Give them Modbus, give them all these communication protocols. Then you can use gateways to create custom logic. So you're still having a system that's being told what to do, and it's pulling data from how it's running to a BAS system. But over here, you have the ability to say, all right, because I have this gateway, I'm going to use if this, then that statements. If it's this cold outside and it's this temperature inside, change the capacity correction of the outdoor unit to make sure I don't ever use more capacity than I need. When it's done, take it out. So all through customizable logic. These data management servers give us that flexibility. All right, so maybe you have a smaller VRF job. Maybe you have one outdoor unit. Maybe you have up to 128 indoor units, right? Maybe you have a couple of outdoor units, because an outdoor system maybe could utilize around 64 indoor units. So you have 128, right? And you want to control them from one point. They all have their own controller in the space, but you want to see everything from one point. Well, utilize a central touch controller, a centralized controller, where you can control and monitor the system. You can schedule it. You can change all the settings, and you can see everything in one controller. Okay, so really great feature. Wi-Fi adapters, right? Okay, I want to be able to control the system through the Wi-Fi, but I don't have a specific brand of thermostat I like. Wi-Fi adapters can help with that. Now, Samsung's utilizes our SmartThings software, and that works for either Android or Apple, other devices. We can control up to 16 units with one Wi-Fi kit. You can program it, you can group them, you can monitor the energy, but you can also utilize the geofencing that looks at when the people are home based on the devices registered to it. So you have 5 cell phones registered to it. It looks at them and says, okay, everybody's home. Let's run to this set point. Okay, everybody's gone. Let's set back. Let's turn off. Okay, goes back to a normal, goes back to that mode where it's using less energy. But then it's looking at the geofence location of those devices, and it says, okay, they're within a certain mileage and they're moving at this rate. Let's turn the system on now so when they get home, it's ready. Geofencing saves energy, but maximizes occupant comfort as well. And then here's those integrators I talked about, their data management servers as well, but you got a BACnet, you've got LAN, and you got options for Modbus. So whatever building management system they have, whatever control system they're used to, we have an integrator for them. Now, this is also really cool. Let's say that they have a building and they've already got an air handler in there. Maybe it's a central station air handler that controls multiple rooms, but we want it to be part of our VRF system. They're going to utilize some VRF units, but they still want to control this unit that might be for the core or for certain areas. You can utilize accessory control boards that go into your existing air handler. Everything ties into it. You add an electronic expansion valve. And what does it do? It takes that existing air handler and makes it a VRF air handler. So we can control it for normal temperatures, central station heating and cooling. Maybe it's an outside air processor where we're bringing outside air and processing it before it goes in the structure, or it's a true dedicated outside air system that does heating and a cold heating coil and a cooling coil to maintain net neutral air. You can do whatever you want with this accessory control board, right? Ours is that universal communication kit that usually takes any indoor unit and makes it universally a VRF indoor unit, giving you the flexibility to maintain designs of a building. Maybe the ductwork's there and it's really hard to get it all out and you have that central station air handler. All right, just make it a VRF unit and tie it to the outdoor system. Now, this is really cool. Now, we do this, and I know some other manufacturers may or may not do it. I can't speak for them, but I know that we do it. If we have a large job that they want to go VRF, multiple systems, and they want to talk on their own language, right? Well, okay, we can open the protocol channel for them to control it. So this is a case study. This occurred at a resort in Japan or in Korea. The building outline, there was 9 floors above ground and 3 floors underground. It was a resort. There were a total of 392 rooms, and they were controlling or they were communicating on an RS-485 network. Their control type was non-NASA, meaning that this was an older Samsung protocol. When we look at the equipment, the outdoor unit, they had 219 single-phase outdoor units and 633 cassette or ducted units in the resort. Okay, so they wanted to control it with their third-party controller. This same controller that controls the lighting, the blinds, the elevator for the structure. Okay, we just opened up the protocol. Now, this unit controls all of the Samsung equipment as well, giving it extreme flexibility to do whatever we need to do. If people think VRF controls are complicated or they're not easy to use, they're not flexible, this couldn't be more from the truth. Okay, we're in the home stretch. I know I've been yakking at you for a while. Let's get to misconception number 10, and that's that VRF equipment, it just stands out. It's too hard on the eyes. I don't want to see it. Well, while wall mount units are more popular globally, You can use them. You can put them on a wall, but there's lots of VRF outdoor units and indoor units that can be made to match the indoor design, right? Okay, look at this. It's a big hotel, right? Look at that roof. Where are you going to put the equipment, right? You're not going to have a lot of room up there. You need a lot of capacity. You're not fitting a ton of rooftops up there, and you're not ducting into it. But look at those VRF systems mounting up there, and the piping is ran underneath and goes right into the building to the individual indoor units. From this space, those units being behind the sign, nobody ever saw them. Right, look at a conference room. 4-way cassettes recessed up in the ceiling. They're there, but they almost blend in with the ceiling, and they keep people comfortable. Here's a kitchen with what we call a 1-way cassette that blows air out of one louver, brings it back into the bottom. Again, recessed up in the ceiling. It's really hard to see. It doesn't stand out like you think it would. And then we get to some really cool customizable ones. Our 360 cassette, it's like a 4-way cassette, but completely circular, has no airflow losses, whatever that look, and all those other features. But look, instead of just being a white fascia panel, you can get it in black to blend into a ceiling, right? A lot of these restaurants we're seeing where they black out the ceiling, well, they got a black condensing unit and they black out the piping with Armaflex insulation. You can't even see the HVAC system. And heck, half the times people see this, they think it's a speaker, right? And then look, ducted units over here, these are sitting up above an attic, and all they've got is a small slot diffuser. They don't see the ducted unit at all. And here's another 4-way cassette in a higher ceiling. They use some compensation settings to allow the airflow to blow farther down, but just still don't see the equipment. It blends in with the space. We're not talking just about wall mounts that hang off the wall. We're talking about products that can really be incorporated into the overall design of the structure. That 360 cassette, okay, you've got a round fascia panel, you got a black fascia panel, they come in square. Get the thing customized and customly printed, to make it look like part of the structure. Imagine walking into a restaurant or maybe even walking into a shopping department that's logo is a Target sign, right? You get what I'm talking about. Imagine if all the air conditioners had a Target logo on them and they were in the ceiling. Not only do they condition the space, they blend into the space, but they become part of the overall branding of the structure. Okay. So here's my key points, right? Properly selected and designed systems are going to perform well in low ambient conditions. The design and installation is simple, and VRF systems are reliable, and they're economical solutions where people are concerned or worried that they won't. We can tackle outside air very easy, either by incorporating into the indoor units or decoupling it with other outside air systems. Heat recovery, perfect control and efficiency in just about any space. And then that wide variety of indoor units allows the system to blend in or enhance the look and feel of today's conditioned spaces. Okay, that's my story, and I'm sticking to it. I want to thank you for joining us today and turn it over for any questions that we may not have addressed. Also, you'll find on the screen my email address. So should you have questions, you want to reach out to me later on, please feel free to do so. So that's about all I've got. And if there's any questions, let's go ahead and address them.
Awesome. Thank you so much, Jose. That was fantastic. And again, if you missed anything while watching it, that's going to be up on the HRAI YouTube page. We do have, 4 or 5 minutes if you want to pop up a question in chat. And like Jose said, his email is up there as well if you want to get to him afterwards. But I think the sign of a good presentation is maybe people don't have questions.
Either I impressed them or I bored them. One of the two.
I don't think so. No. Okay, we'll give it one more minute here. Just for some, and I was commenting on the background of this picture earlier. So do you get to work in places like this, Jose?
Others do. I get to see less than stellar jobs like this. I get to see them in my training centers.
Yeah.
But boy, I'd love to be able to see that from that pool in the background.
Yeah, just it's a good place to relax and do some designing and stuff. Yeah.
And with my design software, I could sit in one of those lounge chairs and connect to the unit, right?
It's working from home, right? It's a remote work. Right. It's the way of the future. So I think we're good. If you have any follow-up questions on these products or this presentation, there's this email there. But I'm going to let you go. And thank you again so much. I'm sure we'll see you back soon.
Thank you, everyone. Thanks for coming.
Cheers. Bye-bye.